Hello, men. This is Mr. Ward with another edition of Physics Coach YouTube. On this first of 3 videos, we're going to take a look at problems 1 and 2 from the friction practice sheet that I gave you guys about a week ago. I'm not going to repeat the problems because you have them on your sheet, but the first problem, we were pulling a block with a applied force of 30 newtons, and we were asked to find the mass. The applied force that you would have to pull with to break it loose, and after you got it broken loose, the acceleration that the object had. So let's start with our usual free body diagram. And so here's the mass, and here's the weight. And upward, of course, we would have the normal force, which would be equal to the weight. And to the right, we would have this applied force, and to the left we would have our frictional force. We're not sure what it is, but we are sure on the first one. We know that we're moving it as at a constant speed, so we have kinetic friction over on that side. So this would be then our free body diagram. Of course, then we would write our F net equals ma, Newton's second law. And in this situation, we know that in the horizontal direction, the object is moving at a constant speed, so we can zero out the acceleration, and we know that assuming that this direction here is a, that the left side of this equation, Fa minus Fk, will be equal to 0. But we have to, of course, replace Fk with something else. And that something else would be UK Fn equals 0. And of course, Fn in this problem, since these two guys here are equal, then we can replace Fn with mg. So we'd have Fa minus UK mg equals 0. Okay, so we have everything that we need. What we're looking for then is m, so we can solve for m. M would be equal to simply Fa over UK times g. Fa is 30 newtons. UK is 0.4 millunits, of course, and g is 9.8 meters per second squared. So we run this calculation through, and what we find is that the mass is 7.65 kilograms. Okay, so that's the first part. That's part B. Part A, of course, is the diagram. Part B is the mass of the object. Okay, in the second part, we want to find out what force is required to start the object, which means that we're going to have to take our Fk here and replace it with F static. Now, usually you would draw a new diagram for this, but to save space here on my tiny little smart podium, I'm going to modify this diagram. So I'm going to put a line here, and we're going to do part C, where we find the force required to start the object. Okay, for the second part of this problem, what we have to do is find out what force is required to start the object from its initial speed of v0. Under these conditions, we would see that the applied force would have to be equal to F static, because when it's greater than F static, it's going to kick over into F kinetic. So we'll just say that those are the conditions needed. And at this point, then A would be equal to 0 meters per second squared also. Okay, so we start out with F net equals ma again. And because A is 0, this term will 0 out. And now we're going to write the forces on the left side of the equation. So we would use the same, free body diagram we had up above, but the Fk would be replaced with F static. So the problem is going to look very much the same as before. So what we're going to see here then is F applied minus F static max equals 0. And replacing F static max with mu static Fn. You don't have to say mu static max because that's what mu static is. And then, as usual, on level ground with nobody pushing off on us, we could solve this or substitute in here mu static mg instead. I'm going to take this up here so we can fit it on one page. So now we rearrange and put FA on the left and everybody else on the right. So that would give us FA equals mu static mg. Mu static then would be 0.6. Mass would be this mass we just got in part B. So this would be 7.65 kilograms. And G then would be 9.8 meters, meters per second squared. Well, that's not going to fit, so meters per second squared. And running this calculation through, we find out that the FA for part C to start this from rest would be 45 meters, which is noticeably bigger than the 30 that we would have to use to keep it moving once we get it started. Okay, so that's part C. Now in part D, this is a different situation. So what we have here now is we're going to keep the applied force at the 45 that we had before, but now after it starts to move. So once we've broken it loose in part C, we're going to maintain that 45 newtons of force rather than back it down to 30 as we had in the first part. And of course, what's going to happen here is that the object is going to accelerate. Okay, so we'll start with, let me draw a little free body diagram over here. So what we would have would be this situation. I'm just going to draw the horizontal part. So this would be FA at 45, and this would be the smaller F kinetic, which we're going to calculate in the problem. And of course, you would have your Fn and your mg in here as well. But the difference here in this one is that A is going to be not equal to 0 meters per second squared. Okay, so back over to our free body diagram, we get the sum of the forces equals ma. And this time we're going to substitute those values over from that diagram, and we're going to get Fa minus Fk equals not 0, but ma. Fk will be mu k mg, and that's going to equal ma. Since what we're solving for is A, all we got to do is rearrange and do that. So we'll get Fa minus mu k mg over m. And substituting, we get 45 newtons minus 0.4 for the coefficient kinetic, 7.65 kilograms, and 9.8 meters per second squared. So your acceleration comes out to be 1.96 meters per second squared. Okay, so that's problem 1, parts B, C, and D calculated. Okay, now let's take a look at problem 2. In problem 2, this is the box being pulled across the floor by a rope at an angle, and I'll put the given down here. Okay, there's the given in this problem. Now the free body diagram here, this one's a little tricky, if you remember. First I'm going to draw the real forces diagram. So on that one we would put our mg down, and normally we would have the normal would be that tall, but remember we're going to have this tension from a rope pulling at an angle, and what that means is that this much of the force in the vertical direction is going to be taken over by that tension. So that means that the normal force is going to be shorter by that same amount. So when we put the normal force in, it's only going to be this long instead of all the way up to the black dot. Okay, so this would be Fn, and this over here would be the tension. I should have that labeled. And to the left, we're going to have Fk. And the problem says this is going to be moving at a constant velocity. So what we need to mark under here is that A equals 0. Now that doesn't mean that it's not moving, it just means it's moving at a constant speed. And what we want to figure out is what coefficient of kinetic friction would allow it to move at a constant speed. And that's the point of this problem. Before we do that, though, this free body diagram here with the real forces in it is not the best place to find what we need for this problem. So we need to break that thing down into a modified diagram. And in this situation, we'll do the easy one first. Mg, the normal force is going to be a little bit shorter. And on top of that is going to be something else. And that something else is going to be the y component of the tension. So this will be over here, F, up here, Ft sine theta. And then the horizontal component of the tension will be Ft cosine of theta. And then back this way, of course, you're going to have the kinetic friction. And that circle diagram is the modified diagram, again with A equal to 0 meters per second squared. Now in this problem, if you haven't done it before, you may not realize that before you can do part B, you're going to have to do part C. You need the normal force first. So to do that, we'll flip over into y direction. So some of the forces in the y direction will be equal to 0. Oh, I'm sorry, let's put it the right way. Will be equal to ma in the y direction. And we know that a in the y direction and the x direction in this problem has to be 0. So then that would show up as Ft sine theta minus plus Fn minus Mg equals 0. Solving for Fn, then we get Fn is equal to Mg minus Ft sine theta. And now we're ready to plug numbers in, so let's do that. We know our mass is 20 kilograms. P is 9.8 meters per second squared, minus the same old 100 newtons of tension, and times the sine of 35 degrees. And that normal force comes out to be 139 newtons, and that is the answer for part C. While we're at it, if you take a look at part D, it says what's the net force on this object? Well, since the acceleration is equal to 0, the net force on it, of course, must be 0. So we'll just get that out of the way. So now all we have left to do is part B. Okay, part B requires us to find the kinetic coefficient of friction as this object is moving at a constant speed. So we'll do the x direction then. Some of the forces in the x direction is equal to ma. Whoops, don't need two equal signs there. Is equal to ma in the x direction. And since that is 0, we'll 0 it out. So looking at the modified diagram up above, we're going to be using this Ft cosine for the horizontal direction, and that would show up then as Ft cosine theta minus mu k times the quantity of this up here. That would be this guy here. Now, since we already did that, you might say, well, let's just plug the numbers in Well, let's not. Let's pretend we're doing this thing from scratch, and we'll substitute in here for Fn. Oops, let me put the right equation up first. So we would have UK Fn here is equal to 0. So the horizontal component from the tension and the friction force pointing to the left, those two would cancel out, add up to 0. Now, let's do our substitutions in symbolic form. So we'll just bring the ft cosine theta down, minus UK times this green circled thing up there, which is Fn. Oops, UK. That would be mg minus ft sine theta equals 0. Now, since we want to solve for UK, let's do that. So we get UK is going to be equal to, if we flip all of this to the other side, and that UK will be negative, positive, so we can say UK equals ft cosine theta, and then bring this back underneath, and we'll get mg minus ft cosine theta. So make sure you know how we got from here to here. You might want to do it in 2 steps, but there it is in 1 step. Okay, now we're ready to plug some values in, and the tension's still 100 newtons times the cosine of 35 degrees. We're going to divide that by the 20 kilograms times 9.8 meters per second squared minus 100 newtons times the sine of 35 degrees. And calculating that out, we get B. For part B, we get UK equals 0.59. 2 sig figs will do for friction. And that's that problem. Some of you may be pretty comfortable with these problems, so instead of just doing 2 of them, I'm going to do the 3rd one. So if you were not sure how to do those 2, now you should have something to study. If you did know how to do it, wake up. We'll take the 3rd one now and see how that one goes. So here's problem 3, the inclined plane problem with friction. Okay, so the story in this problem is that we have a mass sitting on a hill, and the angle of the hill is too shallow to allow the block to break loose because the static coefficient of friction is too high. So what we're going to do is we're going to increase the angle of the hill until we find the angle at which it breaks loose and slides down the hill. Then, after that, we're going to keep that angle and see what the acceleration is. So if you're very clever, you might see here that the answer to that first part might be 35. No, it's actually smaller than that. We're going to put it to a larger angle, actually, not keep it at the angle where it broke loose. Okay, so start with our free body diagram. Here's the mass. Down, of course, would be mg. Now remember, this is a little different. We're on an inclined plane, so we need to draw the normal force perpendicular to the plane and a little bit shorter than the mass. So this would be the normal force, roughly 5 1/6 as long as the mg for a 30-degree hill. And then up here, we would have our F static max. So we're right up to the point where this thing is ready to break loose, but the acceleration at this point is still 0. Okay, we're going to need a modified diagram because this thing's a little more complicated than the previous problems. So I'm having problems with my pen. It needs to be recalibrated. Okay, so our mg sine theta is what we're looking for, perpendicular to the hill. I'm sorry, not mg sine theta, mg cosine theta. And our normal force is the same length, perpendicular to the hill, and that would be Fn. Then down the hill, as always, we have mg sine theta. No matter what, friction, no friction, moving, not moving. Up the hill then, we want our F static max to be just small enough for this to not break loose, but to be ready to break loose. Okay, so this then is our modified diagram, and A is still 0. And now just a little bit more tip up on that hill, and it's going to break loose. Okay, so at that point, we know, at this point, I should say, we know that F is still MA equal to 0, and this is along the hill in the X direction as we've rotated the axes. So this is going to then be replaced with the down the hill component, mg sine theta. So we have mg sine theta downhill. We're going to choose that as our positive direction because that's the direction it's going to ultimately go. And then the next thing we need to put in there is our F static max. And that would go over here. So minus F static max. And since we know that is going to be mu static Fn, let's just plug that in right now. Okay, now we've got to be real careful here because we're on an inclined plane. You should be reminding your brain that that's what we're doing. Mu static, now we have to put in here Fn. Well, we're not just going to put Fn in there, we're going to replace it with mg cosine theta, which is equal to Fn. So it's be mu static mg cosine theta equals 0. Now we can see that the mg's will cancel. So these two guys will disappear. They won't go to 0, they'll just cancel. When you send something to 0, you put an arrow and a 0, we're just canceling here. So you can easily see then that mu static is equal to the sine of theta over cosine of theta. And this is a pretty cool problem because all of this mess here suddenly turns into something very simple, which eventually reduces to mu static equals tan theta. Now, but that's not the answer. What we want is the angle. So what we have to do is one more step to an inverse tangent and say that theta is equal to the angle whose tangent is mu static. So that will be the angle whose tangent is, what is that, 0.42. And when you run that through on your calculator, you get for part B that the answer, theta slide, as I've called it in this problem, is equal to 22.8 degrees. Okay, so that angle is where the breaking loose will begin. Okay, it might be interesting to find what the acceleration is if we use 22.8, but first let's go with a larger one, 35 degrees. And then we can do a quick replacement and see what acceleration would be for 22.8 degrees. We didn't do that in class, I don't think, but only take a couple seconds to do that one. Okay, so net force equals MA. And the only difference in this problem is that the term up here that went to 0, that same term is going to go still equal NA. So let's just save ourselves a little time here. Of course, you wouldn't do this on a test or quiz, but that would go to mg sine theta minus uk mg cosine theta equals NA. So the m's cancel, only the m's, not the g. And that then allows us to calculate A as g sine theta minus uk g cosine theta. And now we're going to replace that with the new value of 35 degrees. So this would be times the sine of 35 5 degrees, minus UK, which is 0.36, times 9.8 meters per second squared, times the cosine of 35 degrees. Okay, so that gives us an acceleration of 2.73 meters per second squared. That's part C. Now, just for fun, let's go back up here to the 28 degrees and put that in these two 22.8 degrees, put that in for these two 35 degrees. This is going to be less than 2.73, of course, but it's not going to be a tiny, tiny little number like 0.01 or something, because the coefficient dropped down from 0.42 to 0.36, so that's going to be a little bit more noticeable. So this would get 22.8 degrees also. Oops, I made a mistake here. There should be a parenthesis here. Let's just throw one in there to be safe, so we have one at each end. Okay, so here's the calculation, and your new acceleration with the shallower angle is going to be, for our new part C, that would be C 22.8, 0.545. So it's not just a little bit over zero, it's a fairly large amount above zero. So that is problem number 3. And that'll be it for today. That'll be it for today for working out problems. Of course, what you should do now is to work on something else. Either look these problems over and see if you can figure out the ones that you had a problem with, or work on something else. The next set of problems we do, that would be on Tuesday, would be problems 4, 6, and 7, I believe it is. So take good notes on those if you need to. If you don't, you can do something else instead. Peaceful and quiet, of course.